Here's another video about exponential functions. And the question I want to address here is, what's so special about e to the x? It's kind of a funny thing if you really think about this. This is a bizarre kind of function. This is 2.78 or 1/8, or it goes on forever, just like pi. They're both transcendental. They're difficult numbers to work with, and it's a little counterintuitive. After all, if you're doing problems with half-life, if you have a half-life problem of something decays in 3 hours or some such like this, it's really easy to write something like that down. You have some amount of stuff initially, and every 3 hours you have it. Any half-life problem you can write down. If you had a 2% growth of a population, you could just write this down. You'd have some initial population. You'd have 1.02 to the t if it's every year, or t over a doubling time or tripling time or whatever. All the kinds of problems that you would see in algebra or pre-calc or whatever, that involve half-life or doubling times or population growth, you can actually write these equations down without having to do any of that logarithm garbage. But usually you're exposed to this function over and over and over and over and over again. And what's the deal? Why? Here's the deal. Suppose we want to model population growth. Now, this may not be the interest of an engineer, but some social scientists, or if you're planning infrastructure, you're just trying to make decisions about the future of your society, this would be good to do. Well, step one might be to do something really simple. The growth might be proportional to the present population. Think about that for a second. The number of people you have, males and females, probably decides roughly how fast you're growing. If you only have a couple individuals and they're reproducing, you can only make a couple more. If you have 1 million people reproducing, you can make millions more. So these are tied together. Well, let's call population something. Let's call this p of t. It's a function of time. And how are we going to quantify this related to the proportional? It's a good question. Well, we might say that growth is equal to some constant times p of t. This might be some constant, related to the species or surroundings, availability of food or whatever. Now, this is kind of simplistic, of course, but we can always make it more complicated later. Now, what's growth? Growth is the change in population per time, right? It's a rate. This is a rate of change. Got a frog in my throat. Rate of change, rate of change, rate of change. Oh, hold on. We're in calculus. The change in population per time is a derivative. All right. So this is what we call a differential equation. We've made some basic assumptions about growth, and we have a differential equation. Now, this is a little different than an algebraic equation. The thing that we don't know is p. What is p? This is the unknown. I don't know what p is. I might know something about it. I might know that initially, I might know that P is some amount. I might start with some initial population. But I don't know what the function is. How do I find that? Well, that's a separate course, differential equations. But we can guess this. What function has a derivative equal to itself, maybe times a constant? If the constant's messing you up, suppose it's 1. What function do you know when you take the derivative, you get it back again? Oh, wait. It's e to the t, right? So let's make a guess. Guess. P of t equals e to the t. Right? And then we try it. All right, let's try it. So if I were to take the derivative of e to the t on the left-hand side, and is that going to be equal to r times e to the t on the right-hand side? Well, almost. I have a pesky r here. Well, all right. Next guess. Guess e to the rt. And try it again. All right, so the derivative of e to the rt equals r e to the rt. What's this? This is chain rule. R e to the rt, question mark, equals, question mark, e to the rt. Yes, this works. Okay, well, we're getting closer. We're actually not all the way there yet. Because I also have an initial condition. And this doesn't quite work there. Third guess, because when t is 0, I need some initial population, 5, 6, a million, whatever. And this does not equal e to the r times 0, right? Which equals 1. All right, so third guess, p to the 0 times e to the rt. Let's try that. So the derivative on the left-hand side, so p to the 0, p naught is a constant, equals, question mark, r, p naught, e to the rt. The derivative goes through the constant, so p naught, d dt, e to the rt, equals, maybe, r, p naught, e to the rt. This derivative, again, chain rule. And yes. Okay, so this most recent guess satisfies the differential equation and the initial condition. So this is where we come up with these population equations, p naught, e to the rt. Right? The reason why math books have all these exponential equations instead of things like 2 to the t or 3 to the t or whatever is because of this differential equation and other differential equations. That's where it comes from. It's an enormously important function in mathematical sciences and engineering. All right, we'll talk more next time.